next presentation, which will be given by my dear colleague Shravan Chunduri. Shravan is the head of technology at Taiyang, and I've been working with him for ages. Almost feels like we already played together in the kindergarten. It's not like this, but since we've both been only working in solar to a certain extent, it is like this. Shravan will talk about updates on commercial HJT cell and module production. And actually, this is also the launch of our heterojunction report. It's the second one. Last year we launched a first report. Now we did an update, talked really to a lot of players. It was a lot of work. We just published it also on our website, so it is for download. Shravan, please go ahead. Looking forward to your talk.
Okay. Thank you very much, Michael, for this introduction. Can you see my screen? Hello? Hello?
Yes, I was on mute already. We can see it.
Oh, okay. Sorry. Okay, because I was thinking that I was not. Okay, so Michael, thanks a lot for this introduction. Hello everyone. Welcome to my presentation. I'm Shravan Chunduri from TaiyangNews. Today I'm going to give updates on commercial heterojunction cell and module production. This is also a launch event for our second edition of report on heterojunction solar technology. So before I really go into the main topic of my presentation, I would like to take this opportunity to provide a brief introduction of our company. We are actually two companies, and we have two platforms. Taiyang is an open platform. We publish reports on advanced PV technologies, and we also publish the market surveys on various production equipment and process consumables. So the differentiation with TaiyangNews is that it is an open platform. That means all the publications can be accessed for free. Whereas Mishko is our consulting arm through which we provide services, of course, at a fee. Our services include communication strategy development, technical research, and market intelligence. With consulting services, we go actually much deeper into the specific topic, as you can see what we do already with our free platform TaiyangNews reports. As I mentioned in the beginning, my today's presentation is a summary of latest report on heterojunction technology. So the first edition was published in early 2019, and actually a lot has happened since then. So the latest report provides a summary of various techno-commercial development associated with heterojunction technology. The report is, as Michael mentioned, it's already available for free download at the report section of our website. We especially launched for this conference. I don't think I have to really go into the details about the heterojunction, but what I would like to emphasize is due to the fairly different cell structure compared to the typical crystalline silicon cell, which is a PERC, heterojunction actually requires a completely different processing sequence and actually line setup. Moving on to the next slide. So it's a kind of a introduction. So what we actually saw last year was companies like REC, Tongwei, GS Solar have actually moved into the commercial production, prior to which most of the companies were rather operating process developments or R&D lines. So this is not including Panasonic. So Panasonic was kind of an exception. But actually, several experts have really thought that heterojunction would be in limelight in this year. Usually, the most of the technology trends are known at SNEC. So that's where people thought that, okay, there would be a lot of emphasis on heterojunction. But during this time, PV industry actually took a rather interesting trick of increasing wafer size. So, end of the day, what really matters for the end customer is watt peak per module. And actually capitalizing on this, PV makers have followed the suit of larger wafers. So, for example, companies like Trina and Ryzen, they have attained module powers up to 600 watts using 210 mm G10 wafers, what you call today. So actually, still heterojunction managed to be in the headline. So of course, few companies have stopped activities, but there is really a new stream of players came in. So that includes not only new to the company, not only new to the industry, but also the well-established players have also expressed interest in venturing into heterojunction. So when it comes to the cell processing, of course, high efficiency cell technologies such as heterojunction actually requires high quality wafers. But as far as the core processing is concerned, there are three important steps. One is a wafer conditioning, deposition, and metallization. So wafer condition is nothing but optimized wet chemical process such as etching, texturing, and cleaning. Of course, I would like to emphasize that cleaning is actually pretty much key here for heterojunction. And the core of heterojunction processing lies in two deposition steps. So one is the core layer, which is nothing but doping depositing the intrinsic and doped amorphous silicon layers, and they are topped with TCO layers. Metallization is kind of a tricky part, as the core layers of heterojunction are high temperature sensitive. A completely different paste system is required, and also contacts are not sintered but cured at low temperature. So the most important trend in heterojunction is heterojunction processing wise is adapting the technology and tools to larger wafer processing, as you would see in the coming slides. Starting with the wet chemical treatment, heterojunction processing is actually no different from the standard. That means the steps are the same, but each step kind of requires a special optimization. In etching, technology requires little more deep etching. Maybe 14 to 18 microns of silicon is etched from both the surface put together. In texturing, most important optimization is the surface morphology, meaning the process is optimized to generate pyramids with low micro roughness and sharpness that favors the subsequent deposition process. Heterojunction actually requires a special cleaning regime. Here there are two methods, RCA and ozone-based method. But I think right now the trend is going towards ozone-based method. So as far as the equipment suppliers, there are really a lot of equipment suppliers like YAC from Japan, Rena, Singulus, SC New Energy, and Exotech. So, and interestingly, most of these wet chemical tool suppliers have really optimized their tools, to support this high throughput, and which is something like 12,000 wafers per hour when referring to M6. But they have also made their platforms to be suitable to process larger wafers, something like G12. And here the throughputs are already at 8,000 wafers per hour level. So coming to the core layer, there have been actually two mainstream technologies, so PCVD and CAT-CVD, during the early stages of development of heterojunction. However, now PCVD seems to be the unanimous choice. But of course, a company called Lead Micro, they are well known in ALD deposition tools for PERC. They also kind of developed a completely different platform called plasma enhanced ALD. But I think coming to PCVD, actually it is currently the heart of the heterojunction processing. So performance wise as well as the cost wise, because as of now, PCVD is currently commanding about 50% of the capex required for heterojunction processing lines. So as far as the tool suppliers, as you can see, applied materials, GS Solar, Ideal Energy, Sunflower, Maxwell, SE New Energy, Ulvac. These companies are offering. Of course, applied materials, they are not typically PV company. These are TFT tools that were refurbished to use in the early days. But I think now more and more companies are, manufacturers are looking for PV specific solutions when it comes to PECVD. But of course, PECVD is also a kind of a bottleneck in terms of throughput. As you can see here, the throughput of PECVD is not so much. So the typical throughput levels so far the companies have achieved is around 5,000 wafers, referring to M6, but actually that's not at all discouraging. This is a very significant improvement compared to last year. But then there is already one company which is offering 8,000 wafers per hour, referring to M10 wafer size. And moving to the next deposition step of heterojunction processing, which is a TCO deposition. Here also there are two technologies. One is RPD and PVD. As you can see from this comparison table, except for high efficiency potential, actually PVD is better in every other aspect, with benefits such as double-sided deposition. But PVD earlier had RPD earlier had one problem, that it was only supplied by only one supplier. But recently, 1 or 2 years ago, SE New Energy has licensed the process for RPD, and they have developed a new high volume high throughput manufacturing system. But RPD always known to give very high efficiencies, but with the developments in the PVD segment also, this gap between the RPD and PVD in terms of efficiency is reduced on continuous basis. So right now I think it's about a 0.2% efficiency gain, and this may even come down in future. And as far as the suppliers, Fonadene, Singlas, and GS Solar are offering the tools based on PVD. The important players, and SE New Energy, as I mentioned earlier, is the leading company that is betting on RPD technology. But again, like with the wet chemical tools, PVD suppliers have also made a tremendous progress. So as you can see here, like Fonadene and also the Singulars, they are offering tools already that can support 10,000 wafers, referring to M6 wafer formats. But if you attend any of the recent presentations, they already say that these tool platforms can already go 12,000 wafers per hour. So RPD is not really as of now is high throughput. It's right now at 5,500, but I think SE Energy is also working in the background to make up this. But SE Energy is also providing an innovative solution, because RPD is a single side process, and they are combining one side RPD and one side PVD, a kind of a mixed solution. And as far as the metallization, there are two main options here: plating and screen printing. Screen printing is mostly followed by most of the manufacturers. However, the current screen printing method has one drawback of using low temperature fluid paste, which requires a higher laydown. Having said that, metallization paste segment made a tremendous progress in reducing the paste consumption. So it's kind of 200 to 220 milligrams. So 80 milligrams is per bus bar, and 120 milligrams is per finger. As far as the application method is concerned, it's mainly dual printing, so which kind of allows a decoupling of printing fingers and bus bars. So excuse me. So as far as the plating, of course, though it is a highly compatible with heterojunction, and because it's low temperature based, and there is also high potential to not even high potential, you can eliminate the silver, but it actually has not entered into the commercial phase yet. So I think jury is still out regarding the plating solution. So then coming to the moving to the module portion of heterojunction, the main change required here is the interconnection process. Ideally, the technology requires low temperature soldering. There is also an option to use electrical conductive adhesives for the interconnection, which is mainly used, out of China, at least during the initial days. But it's not yet clear how the overseas, non-Chinese manufacturers would develop technology, module interconnection technology, when it really goes into gigawatt scale. So as of now, the current state of the art is to use optimized soldering. Actually, an important development here is many companies are seriously evaluating MBB approach if they have already not done that. So the main incentive here is to reduce the paste consumption. Of course, you can also gain some power, but I think reducing the paste is a really low-hanging fruit for heterojunction paste reduction, cost reduction. So what I have not mentioned explicitly here is the smart wire connection technology from Meyer Burger. It is actually is the best bride for heterojunction, but now the company is not selling the technology on open market. I kind of I haven't mentioned much emphasis on this. Before jumping onto the module power, I would like to give a heads up about the cell efficiencies, because I cannot put all the information in this small presentation. So the current cell efficiencies in mass production are ranging between 23.5 to 24%. And as Professor Shen mentioned, most of the manufacturers are really confident and have a clear roadmap to go to 24.5% already by next year. So coming to the module, though we hear industry is moving fast to larger wafers, well, it's kind of a slow for heterojunction. So the mainstream module producers are still based on M2 format. So this information we got from the data sheets of the company. So it's more or less represents the commercial status. But nearly everyone has a plan to move to M6 wafer as of now. The change in wafer size is mostly happening with new factories. So a lot of companies are building new factories, and this is really the key for new factories. So when it comes to the listing, as you can see from here, Ginergy is among the first to move to the larger wafer formats, which is M6. So that's why the company is able to offer highest power of 465 watt per 72 cell, and then 390 watt in 60 cell. This is followed by REC, which is offering M4 wafer formats. Coming to the capacities and capex information, according to our research, the active total installed HJT module capacity by end of 2020 would reach around 5 gigawatt. This is global, and only about 2.6 gigawatt of HJT modules will be produced by end of this year. The main reason for this gap is the utilization rates of these fabs have been less than 50%, because most of the companies are still in the process development, when you equate it to the capacity, in relation to the capacity. And one of the major bottleneck for heterojunction was really high capex, but good news is there is a very high significant progress here. you know, the capex per heterojunction gigawatt line, it was about a billion RMB during 2019. But if you look at today, you know, it was said between 400 to 450, and there are also some news spreading around that it can be offered for 400 million RMB per gigawatt. So this brings to my conclusion. So what I would like to, or what we found in our report is heterojunction technologies increasingly attracting followers all along the PV value chain and supply chain. You know, equipment makers, cell and module companies, material suppliers, research centers, everyone is really taking part in very actively. Of course, it is very interesting to see, though the capacity is less and production is even less, there is a high interest with announcements actually exceeding 50 gigawatt level. That's what we tracked. I think it's more than 50 gigawatt. But a nice ecosystem is actually built around the technology, with more and more number of companies joining the stream. As far as the technology trends specific to the process stations, in wet benches, ozone-based cleaning seems to be the main path to be followed. Core layer deposition, PCVD, is of course the main technology. Increasing the throughput, scaling up the equipment for larger processing area, that means ability to process larger wafers is the key here. I think a part of this has been achieved. I mean, a part of this target has already been achieved. For TCO, PVD is the mainstream, while RPD, I think with important equipment maker like SC, I think it's also going to play an important role. In metallization, screen printing is the state of the art, and reducing the paste consumption is definitely the main trend. So cell efficiencies are close to 24% and are expected to touch 24.5% next year. As far as the wafer sizes, which is the most important topic, so M2 is still the mainstream of the wafers, while first company moved to M6, and first equipment maker already offering a high throughput version of M10 wafers. So at the end, we think heterojunction is entering high volume manufacturing, which is also the punchline of our report. So thank you very much for your attention. If I have time, I can take some questions.
Okay, Shravan, thanks so much. Yeah, very nice. So let's take maybe one or two just on so content-based questions in your report, so that we can discuss questions on the bigger picture later on in the panel. So I think there was one thing on CVD tool throughput. 8,000 wafers per hour in 46 cell per batch. This looks like two tools are needed for capacity. Can you clear this? Can you explain this?
Okay, let me go to my presentation. Are you talking about TCO deposition or PCVD?
I don't know actually what I think I took it from the list.
Okay, I just cannot see the presentation.
Anyway, then maybe the person can clarify that. Otherwise,
okay, so the 144 batch. So I think I'm at core layer deposition. So 64 5000. Yeah, ideal energy. So yes, so they have. I think this is related to ideal energy sunrise sunflower. It's 64, so they have an 8x8 carrier, and they have 5000 rated throughput. But of course, so for PECVD, you definitely need two tools for doing front processing and rear processing. But I think what ideal energy they said is they really reduce. Of course, you can find all these details in the report. They really reduced losses due to the venting and load lock and venting. They reduced the time for the vacuum, and also they improved the automation. So they made the tool much faster. And one should also know that this is the third generation of ideal energy system, which is a dual stack system. So that means they process two wafers in two stacks. So one process chamber is here, and you have one more process chamber down. So you have processing two carriers in parallel. So this is the different reactor design.
Okay.
If you know from the earlier times, this is also the reactor design followed by early silicon nitride deposition systems, which are in line.
Okay, super. Thanks, Shravan. I think we're running a little bit late already, so let's make sure that we don't take away too much from the panel at the end. So thanks again for the presentation. Again, the report is for download on our website. Professor Shen already mentioned there are a few really crucial players